Hi, and welcome to Chapter 11, Interactions in 3D. This chapter will go by pretty quick. We're going to look at interactions in various distances between a point and a plane, between two lines, lines and plane intersections, intersecting a triangle, look a little bit at reflections, and then more intersections. Finally, we'll end with Gram-Schmidt and creating orthonormal coordinate systems and the terminology for the chapter. So, just as a motivation, think about this in terms of ray tracing. If I have a set of objects out in the 3D world, I want to interact with them. I want to be able to draw a nice computer graphics rendering of them. One way of doing that is through ray tracing, where I send a ray of light out into the world. I see what it interacts with, and then I can get specularities and shadows and a bunch of other stuff. We want to be able to build these things, and so the real two most important things we have to do is be able to interact by computing where things intersect with things, and then also be able to compute surface normals because that affects how light behaves with those objects. So let's start with distance between a point and a plane. Given we have a plane represented as n dot x plus c equals 0, point plus plane, normal form, and a point P, we can ask what's the distance of the point D to the plane, what's the closest point to the point Q on the plane. So that's similar to the foot. We can ask what's the projection on the plane of the closest point. And those two questions are actually relatively easy. Give it a thought. You know how to do this already? Well, to get the distance, first we recognize that, of course, we're going to find this point. P and Q must be perpendicular, just as they were with the foot of the plane. So it has to be parallel to the plane's normal. So therefore, I can write P is equal to Q plus T times N. Whatever that point Q is, it has to satisfy that property. Now our goal becomes find T, and we can simply make sure it satisfies the plane equation. So we're going to take n dot, what was Q, now P minus T times N plus C equals 0. That tells us that T is equal to C plus N dot P divided by N dot N. And if T equals 0, you're on the plane. If you're positive, you're above the plane. If you're negative, you're on the other side of the plane with respect to the normal. So just to put that in a numeric example, imagine we have the plane x1 plus x2 plus x3 minus 1 equals 0, sort of over here graphically. This is a plane along that diagonal in space. And then we have the point 2, 2, 3, and we want to ask, how far we are from the plane. You stick that into our formula, and you'll get that t equals 2. So we're 2 units away from the plane. And then with t equals 2, I can go back and compute the actual q. The closest point on the plane is 0, 0, 1. So if I have a ray and I ask how far away from the plane, I can now do this. Getting the distance of the plane, you can just put that point P and Q back in. D is equal to the distance between P minus Q, which is equal to T times N, which is just equal to T times the norm of N. If N is normalized, then the distance is just T. T was our distance. If T is greater than 0, you point away from the plane. In the same, you point towards the point P in terms of the normal. And if it's T is less than 0, then N points away from the point. This can be useful for deciding what side of the plane I'm on. If the point is very close to the plane, again, anytime we have a test for greater than 0, recognizes we get really close to 0, we're going to have some problems. So it may be hard to decide what side of the plane it's on. Okay, so now what? Well, now let's imagine I have two lines in space, and I want to ask, how far apart are they? As we've already said, two lines in 3D generally do not meet. Such lines are called skew lines. And then we could ask, what's the distance, the point of closest approach between those two lines? Again, we're going to represent them in our parametric form. Here we have point plus s times a vector. We're now the vectors in 3D, so we have 3D parametric lines. And we want to find the point x1 that's on the line L1 that is closest to L2, and the point x2 on the line L2 that is closest to L1. Because we're looking for this closeness again, we know that it's going to be perpendicular, so the vector x2 minus x1 is going to be perpendicular to both L1 and L2. So we can set up a system of equations. x2 minus x1 times v1 is 0, x2 minus x1 times v2 is 0. Take those two equations, expand them out, and then we get two equations and two unknowns, s1 and s2. This is a 2x2 linear system, so you should just be able to go ahead and directly solve it. So given two lines, here we have 0, 0, 0 plus s1 times 1, 0, 0. So this is going through the origin and going up the vertical axis, plus 0, 1, 1 plus S2 times 0, 1, 0. So now we're going along this axis and we're offset along the axis. So think of this as another face of the cube. And then from that, we put that into our linear system. We're going to get 1, 0, 0, minus 1 for S1 and S2. We solve that. We get S1 is 0, S2 is minus 1. And it tells us that the two closest points are 0, 0, 0 for X1 and X2 minus 1, which is 0, 1, 0, which is also easy to verify that this is where these two lines are going to be closest. One's going along this axis, one's going along that axis, and where they actually are closest are along that particular axis. So if the lines do intersect, then X1 will equal X2. With floating point calculations, they may not be perfect. With round-off error, we're going to decide that if they're within some tolerance, say X1 minus X2 squared is less than 10 to the minus 6, then they've definitely intersected. So that gives us a test for if two lines are intersecting in space, which generally doesn't happen, but we can always compute it if we want to. So a condition for two lines to intersect is that V1 and V2 and P2 minus P1 must all be coplanar or linearly dependent, which means that I can also look at the determinant of V1, V2, and P1, P minus 2 equals 0. And that's another way I could look at this. Numerically, it's actually safer to compute the distance between X1 and X2 than to try and decide if the determinant is actually equal to 0. And the reason for that is the number of calculations that go into the determinant are a lot more. So anytime we have a bunch of calculations, we increase the amount of round-off error we can have. So in this case, distance is more tolerant than volume, because volume generally takes a lot more calculations. The errors get multiplied. That's just a general rule of thumb. And anytime you can, fewer computations are likely to have less numeric instabilities. So now let's come back to where we started this idea of ray tracing. Well, with ray tracing, the basic idea for one of the two basic ways for rendering in graphics, we think of the scene as a bunch of planes, in fact, probably a bunch of triangles. And we're going to light the scene by tracing a ray of light from the scene. So if a ray starts it by eye, it travels in a straight direction. I choose some direction. If it intersects a plane, when it intersects the plane, two things happen. It can be reflected. It can also be refracted if it's glass or transparent material. And as it does that, the surface normal of the surface plus the ray of intersection determines everything that's going to happen with respect to that. So that means I need to be able to, given a plane P, which we're going to say represent in point plus normal form, and a line L, point in vector form, we want to ask what's the intersection point? Where does this line hit this plane? So if it's going to intersect, we know that it's going to be on the plane. So that means x minus q dot n will be equal to 0. We also know it's going to be on the line, so we know that x will also have to satisfy p plus t times v. And so now we just want to find t. Right? This is equation. We have two equations. We have solve for t. We plug x from one equation back in the other. We solve for this, and we get that t is equal to q minus p dot n divided by v dot n, as long as the line is not perpendicular to n. This will be okay. Can't divide by 0 otherwise. So that x is equal to p plus, I would just put in t times v. If n dot v is not to 0, if it's very small, this is going to be a very unstable calculation. And if you think about that, what does it mean if n dot v is very small, or 0? What it means is I'm trying to ask for a ray that's almost parallel to this plane where to intersect it. And small errors will make it intersect either here or possibly in New York, because the plane's almost level. And so a small error in the line and it shoots way off into that space. So if to put this in numeric terms, imagine we have, again, the same plane, x1, x2, x3 minus 1 equals 0. And now we have a line, 1, 1, 2. Plus t equals 0, 1, 1, and we want to sort of run along the z-axis and figure out where we're going to intersect this plane. So we need a point q that's on the plane. Well, we can always generate a point q that's on the plane by just setting x1, x2 equals 0. We're going to solve for x3. That's our equation. That results in x3 equals 1. So now I have a point q. I have to get that. Now I've got q minus p dot n. I can divide it by v dot n, where again here we have v. We get n by looking at the first coefficients of those planes. Remember, n is given by the coefficients of x1, x2, x3. and that'll, when we do that computation, we'll just get that t is equal to 3. And then the point of intersection, we plug this back into our parametric line, and we get that the point of intersection is 1, 1, minus 1. And a little fast, but you should be able to go back and review that if you didn't see where all those algebra came out of. So if we're intersecting a plane line when the plane is given in parametric form, we have to satisfy in parametric form, right? Our plane, remember, was Q plus a constant U1 times R1 plus a constant U2 times R2. We also know that X is going to be on the line, so we can stick that back in, which lets us say that P plus T times V is equal to Q plus U1 R1 plus U2 R2, where R1 and R2 are the two vectors that define the plane parametrically. This gives us three equations and 3 unknowns. We can then just go ahead and solve that algebraically and get a different solution. Alternatively, you can actually take the parametric form, convert it into implicit form, and then solve it in that form as well. So when we're doing ray tracing, we're normally actually trying to intersect a ray with a 3D triangle. Triangles turn out to be the easiest way for us to represent lots of things in space. 3 points always define a plane. 4 points may not be on a plane, so it's every triangle is a planar facet, which makes it easier to deal with. So given a triangle P1, P2, P3, an array P and V, we want to find the intersection. That is, we want to find T to satisfy T plus P plus TV is equal to P1 plus U1, where here we have the vector, one of the two vectors of the plane, here we get the second. So by subtracting off the corners of the triangle, we get our vectors to put it in parametric form. This gives us 3 equations and 3 unknowns, and the intersection point can also be determined in terms of barycentric coordinates as U1 times P1 plus U2 times P3 plus 1 minus U1 U2 times P3. Notice this is true, this is in barycentric coordinates, so it all depends on the 3 points P1, P2, and P3. This tells us where it intersects the plane. We actually don't know if it intersects the triangle unless we also test if U1 and U2 are less than 1 and U1 plus U2 equals 1. Right? They have to satisfy this, otherwise it's outside of the triangle in its barycentric coordinates. We'll talk about that, triangles and barycentric coordinates again a little bit later. So given a point X on a plane and an incoming direction for V, we want to now ask what is the reflection or the outgoing direction. Light has this property that it comes in at an angle and it goes out at an angle equal to the incident angle with respect to the surface normal. So n is what we call the angle bisector of V and V prime, which tells us that minus V dot n is equal to V prime dot n. And from the symmetry property, we know that C times n then is equal to V minus V prime. We can put this all together and then solve for C, and we get that solving for C, we get C equals minus 2V dot n, and therefore V prime is equal to V minus 2V dot n times n. Right? So 2V dot n gives us a scalar, which we can multiply by n. Now we subtract 2 vectors, and that gives us this reflection off the surface. So again, by working in linear algebra space, it's relatively easy for us to think of in 3 space, this ray is coming in, and where is it going to go out on? Just give me a surface normal. We can stick it into this formula, and very quickly we get a dot product and a subtraction of 2 vectors, multiplying the subtraction of 2 vectors, and we get our new outgoing direction. So it's pretty easy to trace that ray. Comes in, bounces off. If you want to do refraction, where you're looking through materials, it's a little bit more complicated because now it depends on the index reflection of the surface, Snell's law, but it's also still not that hard. It just adds an extra term in it. So it turns out that that's even easier to look at in a different form. I can also look at V prime equation, and now I can see that 2V dot n is the same as taking V transpose times n. And now I can rearrange this equation of V transpose nn is equal to nn transpose V. And it turns out that nn transpose, which we've seen before, we called it UU transpose when we saw it last time, is a projection matrix, which has the property that it's orthogonal, symmetric, and dyadic, rank 1. And this is actually called a householder reflection or transformation. And it has the very nice property, but now you can see that we can look at it differently for any surface normal. I can also view this as a matrix transformation. Now in practice, we're not necessarily going to want to do it this way because here I have to have the cost of doing n times n transpose gives me a 3 by 3 matrix that I have to multiply by v, as opposed to doing 2v dot n, where I have to do multiply and then a dot product, which is actually computationally a little bit cheaper. The reason of sort of showing you this relationship is because in Chapter 13, which we'll do in 2 weeks, we'll be looking at the household methods in a more general way of how to solve linear systems. You'll see that it's related to this calculation. Okay, the next intersection to do, just to sort of complete them, is, well, what happens if I want to intersect 3 planes? So given 3 planes, they define a unique point in space, and I want to find that point. That is, if the planes are not parallel. So given 3 planes, I write out the plane equations, we ask where they intersect. By just looking at these plane equations, we can put it in matrix form. We get n1 transpose, n2 transpose, and n3 transpose, so we get a bunch of row matrices times x1, x2, x3 equals the 3 different constants. 3 equations, 3 unknowns, we have a matrix. Now we just go ahead and solve for that, and that'll give us a point x that lies on each of those planes. So to fill that in with a numeric example, given the plane x1 plus x3 equals 1, so it's actually on the x2 axis, the plane x3 equals 1, so that's a vertical plane, and x2 equals 2, horizontal plane, so we have this sloped plane and 2 parallel planes. That gives us a linear system that's relatively easy to solve, and that gives us that x1, x2, x3 equals 0, 2, and 1. Now again, to check your equations, your solution here would always be good. You can take each of these 3 points and check that it is simultaneously on all 3 of these planes. So in fact, you can see for this solution it was pretty easy. x3 equals 1, has to equal 1. x2 equals 2. So the only question was what was x0, and since x3 is 1, we get x1 plus x3 equals 1. We actually can see that x1 has to equal 0. So we can solve this by just algebra, but we wanted to see it in terms of the standard form. We put it in matrix, solve for it by Gaussian elimination, and get an answer. But there is a special case if we're given planes with normals n1, n2, and n3. Here we have that n2, this normal, is linearly dependent on the other 2, so that the planes, when the planes are linearly dependent, they don't intersect at one point. In fact, now it depends on what's the rank of the 3 by 3 matrix we get. If this matrix is of rank 1, then we're going to intersect, and they're all going to form on a line. If it's rank 2, they're going to intersect and form a, if they're rank 1, then it forms a plane. If it's rank 2, then they're going to form a line. It's only if it's rank 3 do they form a point. Intersecting 2 planes is actually a little bit harder. We only have 2 constraints. So given 2 planes, we can write them out as n dot x plus c, m dot x plus d. We can find their intersection, and their intersection is going to be a solution of the form p plus t times v. So think about how you're going to solve this. Well, there actually are 2 different ways of solving it, at least. One would be to think about this in terms of what do these planes mean, and what is the line. So I want to find the line v that lies in both planes. That means it has to be perpendicular to both normals, m and n, which means actually v is pretty easy. I just take v as the cross product of n and m, and it gives me the right direction. Now, that's not everything. That gives me the vector. I still have to have a point that's on it. So I want to construct an auxiliary plane that intersects both the given planes, and that is, I know that v dot x is equal to 0. This has got to pass through the origin in terms of the normal line, so it's perpendicular to the line of intersection. It's going to have to be over here. So this allows me to then solve for the constant that goes along with this line. Any point on the line is okay, but I'll just choose the one that's closest then to the origin. So now we're going to turn to something that's not quite as obvious how it's going to be useful, but it is used. In fact, it was used when we did eigenfaces, because when you're doing eigenvalues, you're trying to find an orthonormal set of vectors that satisfy the properties of eigenvectors. There are other times when you want to form an orthonormal set, and you don't want to form them in terms of their eigenvectors. A more general problem is given 3 vectors, v1, v2, and v3, find a sort of close, in some sense, orthonormal set of vectors, b1, b2, and b3. And in general, in fact, we're going to solve this in n dimensions where it becomes useful. We want to take a set of vectors and then figure out what is the orthogonal subspace that they span and get a basis for it. This technique is called Gram-Schmidt, and I'm going to cover it pretty quickly. In terms of the exams and what you need to know what Gram-Schmidt is. I'm not going to expect you to be able to do it. It's something that should be coded up if you're going to really do it. doing it by hand is more just understanding the high-level ideas. But there's also some nice ideas here that you want to sort of see. So the key idea is that orthogonal projections and orthogonal complements can be very useful here. So if I form some space, VI is this subspace formed by V1, I can think of the space V1, V2 as a subspace formed by V1 and V2. And then what I'm going to want to do is, so the subspace formed by V1 and V2 is not orthogonal. I'm going to make them orthogonal by projecting V2 into where V1 was. And you remember that because these are linearly independent, I can always project V2 onto V1, and I'm going to get something. If they're orthogonal, I'll get 0. If they're not, I'll get something that's there, and I'll subtract it off. In terms of what we're going to do, just keep the math a little bit easier to write, we're going to refer to normalizing a vector W by whatever W is as W divided by the norm of dot. In this case, the dot says just take whatever's above the fraction, normalize by that. So let's first look at it graphically, then we'll come back to the algebra. So I have my three vectors V1, V2, V3, and now I want to do this orthogonalization. So I'm just going to start with V1 and V2. I'm going to project V2 onto U1, orthogonalize it, so I can make U1 orthogonal. And I can then use that to figure out, by subtracting off the orthogonal component, I can make a U2 that is orthogonal to U1. And now I got U1 and U2, they're orthogonal. Now I got to handle the third one. I'm going to do this by first projecting it onto U1, figuring out what is that length of the orthogonal component, subtracting that off, right, where I'm going to subtract the orthogonal separation. And now it's orthogonal to U1. It's not yet orthogonal to U2, but I just play the same game. I project it, I figure out what that length is, and then I subtract that from V3 prime now because I'd already changed V3, and that gives me my third vector. So that's the basic idea of Gram-Schmidt, is to project and then subtract off stuff to make them orthogonal. So now let's do it in a numeric example, and we'll summarize what the algorithm looks like. So if I'm given V1, V2, V3 as these three vectors here, the first thing I'm going to do is compute B1, our first projection. I'm going to do that by projecting V2 onto U1. And when I do that, where do I get that from? Well, I can take that from the dot product. So now I'm going to get U0 minus 2, 0. Oh, actually, first I'm going to normalize just so I have a unit normal vector. So I'm going to make the U1 or B1 vector unit normalizing. Now I'm going to take the projection of V2 onto that subspace. So to do that projection, I'm going to take the dot product of V2 and V1 multiplied by V1. Right? That's just the dot product to give me this length here. And that turns out to be equal to 0 minus 1, 0. And now I want to get my U2, my B2, which is the component of U2 orthogonal to U. So I'm going to subtract V2 minus this projection, and then normalize that, and I get that to be 1, 0, 0. And then finally, I'm going to project V3 onto the subspace spanned by V1, V2. And so when I do that, I'm going to get the projection, which is actually going to be the projection of V1 onto V3 plus projection of V3 onto V3. So I get the dot product of V3 with V1 times V1 plus the dot product of V2 times V2. And that gives me this component. Now I subtract that from the original V3 and normalize, and I get 0, 0, 1. Now you might look at this and say, hold it, I got 0, 0, 1, 1, 0, 0, and 0 minus 1, 0. Why don't I just say that if they're linearly independent n dimensions, I'm going to just take the n-dimensional unit basis vectors? Well, in fact, this example shows you one reason why not to. This vector is negative. In fact, any of the axes could have been negative. And so it's important to understand what's the axes when I do this projection that is close in the same direction and also helps maintain the handedness of the system. So to summarize the algorithm, B1 is V1 normalized. I create B2 by subtracting it, and by projecting it and then normalizing it. So B2 is V2 minus V2.B1 times B1, and that whole thing then normalized by what's on top. Then I create B3 from V3 as a thought subspace. I do it again for V3 minus V3.B1, B1 minus V3.B2, B2, and normalize the whole thing. So now, in 3D, this is actually not the fastest way of solving stuff, but it sets up a pattern. Can you guess what it would be if I wanted to do this in 4D and I had one last component, B4? Yep, B4 would look like B4 is equal to V4 minus V4.B1 times B1 minus V4.B2, B2 plus v4 or minus v4 dot b3, the whole thing normalized. So and we want to put these all together. The examples, in fact, in 3D, it's a lot faster to do the cross product. But the real advantage of this is when we go to higher dimensions, when we don't have cross products, and understanding it in 3D makes it pretty easy to see how it goes in 4D. So finally, for the terminology for this chapter, make sure you understand distance between a point, distance between two lines, line and plane intersection, triangle and line intersection, reflection. All those, you should know how to do those as mathematically. Householder matrices, you should know what they are. Understand the processes for intersection of three planes, intersection of two planes, and Gram-Schmidt organization, have a high-level understanding of what's going on. For all of these, if you're looking for more practice, again, as always, there are questions at the end of the chapter you can do. For Gram-Schmidt orthogonalization, if you really struggled and you want to understand it deeper, there's a nice con video as well that'll go through it much more slowly in terms of understanding how that part works.